Good morning and welcome everyone to the seminar by Belén Rodríguez-Fonseca. Belén Rodríguez is going to talk about tropical basin interaction and global impacts, but before starting the seminar, I wanted to say a few words about her career. She is a doctor in physics by the University Complutense of Madrid, where she is working as a full professor since 2010. She has a vast experience in tropical and extratropical climate variability and a record of national and European projects dealing with tropical Atlantic variability and teleconnections. She is interested in multi-decadal modulations of the interannual climate variability, not only in the Euro-Atlantic region, but also in the tropics, including impacts on health and its predictability from the ocean and agriculture. She has a lot of collaborations, and in particular from 2011 she has an active cooperation project with Senegal, advising PhD thesis and researching in climate services in Africa. She has participated in more than 20 projects. She has a lot of publications, and also important to say that apart from these research activities, she is very interested in the dissemination of climate variability and change to the society from primary school to students in the university. She is coordinator of the Meteolab virtual workshop, and she is also coordinator of the Master in Meteorology and Geophysics at the University Complutense of Madrid. So it's a pleasure to have you here. Thank you very much, and now it's time.
So thank you very much for inviting me. I'm very happy to be here also because I see some familiar faces, friends from physics when I was studying, very close friends of mine, and also I see here Julian, who was in our group, and now is here working in CSIC with a group here in Rocasolano. So I'm very happy to have this opportunity. And I want to start with this picture of the group. We are a Tropa group. We call Tropa because tropical Atlantic, but we are not just working in tropical Atlantic, we work in other regions of the ocean, especially in the tropics and the impact all around the world. We are a group mainly of women. It's strained in the Faculty of Physics. The permanent, we are women. And now we are this Veronica is not now, but we are just, we and all of the people that I want to mention that are in collaborating with us in Senegal, in the University of Dakar, that are also part of the group, and I want to mention also their work. So I'm going to talk about a new paradigm of research, and because we are very proud of being part of this new paradigm, because we start with one of the results starting this paradigm. And I want you to show you this satellite image, they are colored image, of the event of 1997, 1998. There was an El Niño event. El Niño is, for the people that don't know it, the ENSO is a phenomenon in which the SSTs, the sea surface temperatures, reach values above the normal values. So when the ocean heats, it's called El Niño, and when the ocean gets cooler, it is called La Niña. And this is one of the most relevant events, 1997, 1998. After, we have another one in 2015, 2016. Now we are having a La Niña this year. That is the responsible of this anticyclone, permanent anticyclone that we are having, because all the models predict that the wave, the extratropical waves that is triggered from the Pacific, is responsible of the anomalous anticyclone we are having. Because of that, we have this weather. So during this 1997, 1998 event, there was this warming. It started more or less in the summer. We can see this warming here and develop, and it reached its peak in December. And the impacts of this event were worldwide. I mean, floods in Peru, dry events in Australia and in the extratropics, also affecting upwelling ecosystems, crops, malaria, etc. But in that year, all of the satellite image and all of the news were focused in the Pacific. There was all the image you are looking. If you look in the reference and the bibliography and the pictures given by NASA, this is from GPL laboratory of NASA. The image were focused in the Pacific, and nobody was paying any attention of this anomaly here in the Atlantic. This cold anomaly here in the Atlantic. So this is the topic of my research. How these anomalies were crucial, and if you know these anomalies with time in advance, you can predict El Niño. And if you can predict El Niño, you are predicting the most important mode of variability in the global climate at interannual time scales, because I'm talking about an oscillation that has a periodicity of 4 7 years, and every 4 or 7 years you have El Niño or La Niña, but it's an oscillation that drives seasonal forecasts. What is going to happen from one season to the other is mostly driven by El Niño. So let me tell you a little bit about the tropical circulation. Here are the winds. I don't see if you can see, because I don't have my glasses, so I don't know if you see it. There are these arrows, are easterlies, there are the trade winds, and the velocity of the trade winds, is in shaded. But what happened here is that these winds, they have an effect over the surface of the ocean, which is to peel up the water in the western area. So the water in the western area is warmer than in the eastern side. And by continuity, the water from the bottom of the ocean arises in the eastern side, because all of the water in the surface go to the west. So do we have this east-west contrast? And this area in the Pacific, it is called the warm pool, Pacific warm pool. And in this area, there is a lot of convection. So the air evaporate and lift and rise the top of the atmosphere, and by continuity again forms this cell, which is called, this is height, this is called the Walker circulation, and close in the eastern side, and again peel up the water to the western Pacific. So we have this Walker circulation, and if you go to the bottom, to the ocean, and you look in the interior of the ocean, in the equator, this is a transit, what happened, this is in meters, the height, is that in the first meters, like 100 meters, the water is peeled, and you see it in the first layer. There's a warm water peel up here, and warm and cold water in the east. This area that separates the cold waters from the warm waters is called thermocline. And when we want to model El Niño, we just use this kind of line of maximum gradient of temperature to formulate an oscillator. So if the winds blow stronger, more water is spilled in the west. If the winds are weaker, then the water goes to the east, and you have El Niño. So it depends on the winds. You have El Niño or La Niña, and you have these oscillations that are driven by the winds. And it's a very coupled model, a coupled mode of variability. So whenever the winds get weaker or the water gets warmer, these oscillations start to occur, and we have El Niño or La Niña. So this is the Death Valley and the Atacama Desert. This is a very nice area of the world, because these deserts, the Death Valley and the Atacama Desert, but also the Kalahari Desert and the Sahara Desert are located in front of these regions of cold water, because the warm water go because of the winds to the west. So in front of the desert of all of the world, there is a region with cold waters, and these are the regions of maximum productivity, where are all the ecosystems. Most 90% of the fisheries are concentrated in these regions. So when you know the Saharan bank, you know, in Peru, there is the anchovies, there is a lot of fish here, and in California, it's very, very important, the fisheries also there. And for example, in Spain, we have Pescanova, who has all of the flow, all of the platforms for fisheries in front of the Namibia. You go to Namibia, everybody knows Pescanova. So what happened? In 2016, the desert, November 2015 to January 2016, this desert appeared full of flowers. There was a bloom of flowers. And this is because of El Niño, because in this region there is no water. And because of the anticyclone of the circulation, the water is only in a kind of clouds that dissipates because of the solar radiation. They are only in the first hours of the day. If you go to Canary Island, you can see like a moist in the air, like, I don't know, fog. You can see fog, but during the day it dissipates. Also, it happens if you go to California, because of this upwelling region, this cold water, but when the anticyclone develops, it dissipates. So when El Niño happens, the warm water goes to the east and rains. And it only happened some of the Nino events, not in all of the Nino events. This was very famous, was in all of the news. So what happened in 2015? This is the anomaly of the sea surface temperature. And it reaches 3 degrees. Well, here people, you are physics, so you are not going to be, but people, when I normally explain this in the school, they say 3 degrees, this is nothing. And I say, well, when you have fever, you only have 2 degrees. Your temperature only rises 2 degrees. So the ocean has fever. I mean, and the energy has a disequilibrium because of this warming on just for 3 degrees. Here it saturates in 3 degrees anomalies. And here we can see in this event how it was in depth. So we can see 6 degrees, like around 100 meters, but in surface it was also these degrees. And only in the first meters of the ocean, because as I told you, there are 2 layers in the ocean. Both the deep ocean, which doesn't know that the atmosphere exists, and the first layer, and this first layer is interacting with the atmosphere all the time. So this layer gets warmer when there is El Niño, only in the first 100 meters, more or less. So in these 100 meters, how much energy is stored? So using this very simple equation, we can calculate the energy, multiplying the mass of the ocean by the heat capacity and the anomaly of temperature. The mass is volume density multiplied by volume, so it's a problem of volume. What is the volume of ocean we have here? So I just took this little square here, this little region here, and the first 100 meters of the ocean, and calculate the volume of this mass water, and I obtained 4.1810 power 21 joules just for 1 degree. So this is hundreds of thousands of megatons, thousands of hydrogen bombs when there is El Niño. This is the heat storage by the ocean when El Niño occurs. And it's getting warmer, 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 and suddenly the equilibrium with the atmosphere is broken, and then this energy starts to be released to the atmosphere and change all the global circulation. So, for example, when the ocean gets warmer, the air goes up to the top of the atmosphere, it goes to the east of and to the west, but also to the north and to the south. And when it goes to the north and to the south, the radius of the Earth changes. So this changes the momentum, and there is a change in the velocity, and some waves are occurs, and these waves can reach farther areas, and these are called teleconnections. These waves that are triggered from the anomalous divergence of the winds in upper levels in the atmosphere due to an ENSO. So, well, due to this teleconnection, we have very different impacts all around the world. So, the impact of La Niña appears in the top, and the impacts of El Niño in the bottom. And we have impacts, you can see, all around the world. For example, in this figure, there is nothing in Europe, but there are strong impacts of El Niño in Europe, but these are the most famous and more robust. These other, we are working in this area, are not stationary, and it's a very complex problem, because we deal with different variables. For example, the mean state, the change in climatology, and other things that makes this problem non-linear, and it's difficult to predict. But in the other regions around the tropics, the problem is very linear, and the impact of El Niño and La Niña are almost the opposite, one to the other. And for example, the most remarkable are these strong precipitation over South America, and dry in the Australia for El Niño, and the opposite for La Niña. And also, for example, it has impacts, very strong impacts in rice production, because if there is no water in regions like in China, where the rice, you need water to the rice to grow. And also, for example, in Sahel, El Niño produce a strong subsidence and no precipitation. And this produce changes from agriculture, energy, and, for example, in malaria outbreaks, because malaria depends on the ponds, and the ponds depends on water. So, coming back to this paradigm, until 2007, normal science has not thought about other ocean basins impacting on ENSO. Until well into the 2000s, research centers focused on El Niño and the impacts of the Pacific El Niño on global climate. Everybody thought El Niño is the driver. There are not other drivers. There was almost no work on the impacts of other basins on El Niño. How other basins? Because if from an energetic point of view, it was not sustainable. They say, well, the amount of energy that the Pacific is able to release is not going to be counteracted by other basins. So you look at the bibliography, there are almost no work. But most of the work, we're talking about this teleconnection I was telling you before. So there is warm water here, strong upper level divergence, so change the momentum here, and then there is a wave. There is a wave that reaches for example, this is for the North Atlantic, and El Niño can produce a weakening, for example, of the trade winds and warm waters in this region. But this is one of the teleconnections. But there were no work about how this area could affect into El Niño. But in around the 2000, there started to be more data of satellite, more data in which you could study with more precision these processes. Well, suddenly we start to work in the African monsoon, and we start to work just in the Atlantic in our group. And we saw that there is a mode of variability in which that is called Atlantic Niño, that is very similar to El Niño in the Pacific, but it occurs in the Atlantic. But the Atlantic is very small. So, well, you cannot see all of the big impacts of ENSO in the Atlantic, but you can see some similarities. So when there is El Niño here, an Atlantic Niño, what happens is that the pressure here diminishes, and there is more pressure in the overland. So the pressure goes to the, from the north to the south, and the rain is in the equatorial band. But when el Atlantic Niño is in the opposite phase, it is colder, there is more pressure in the ocean than in the land, and the rainfall goes to the north. So it rains in the north, it rains in Sahel, it rains in this region which needs water every year. So we were working about this, about how the SSTs, the sea surface temperature of the ocean, could be used to predict rainfall in the Sahel. And well, we start to work and we detect this mode, and we decide to correlate it with the global SSTs of the ocean. And we found, here is in black and white, because this paper was in black and white, but you can see more or less here, that this signal, there are the contours of the SSTs in the Atlantic, appear together with the opposite sign in the Pacific. And we start to say, well, this signal is very related with the signal, but in the opposite phase in the Pacific. And indeed, we look at the impacts on rainfall. And we saw that before the 70s, when there was an Atlantic Niño, there was this mechanism I was explaining to you. The rainfall was stronger in the equatorial band and less rainfall in the Sahel. But after, there was a different impact. And this, we thought it had to do with this influence of the Pacific. So we published this paper after, in which we compare the global picture of the Atlantic Niño before the 70s and after the 70s. So before the 70s, an Atlantic Niño appeared isolated for the rest of the tropical basin. It was an internal mode of variability of the ocean. After the 70s, Atlantic Niño appeared together with an opposite phase of the Pacific ENSO. So this was a very a strong fight we had with the Nature review journal, because they accept us, but suddenly they start to ask for more simulation, for more things, and at the end they say no, we don't accept it. And then we publish in Geophysical Research Letter. The first result was in 2007, and at the end we published this in 2009, but in another journal. And what we found is that there was a very different impact. This is the correlation, black correlation, in different decades. Each square is a decade. And this is when El Niño is leading, the El Niño is lagging. So when the Atlantic is leading, so there is a correlation that Atlantic Niño warming is correlated with Pacific La Niña, the opposite. Okay, so after this decade, which is around the 70s, there was this signal. Well, after this paper was published, I mean, Julian is here, you know the story. Other groups, for example, in Germany and in the United States, they run their own models. We did this paper with people in the ICTP, because we didn't have a model to do it. And it's Fred Kuchaski, and this is a very conceptual and simple model, and we obtained the same results with the model, but they don't accept us this paper. But after this work, using other models, more famous model, more validated models, they obtained the same result. So the paradigm it was open. I mean, everybody was saying, well, there are other basins that are taking an impact, having an impact in El Niño. The mechanism is very simple. It's just through the Walker circulation. When there is an Atlantic Niño, there is this anomalous heating in the Atlantic, produce like the vertical velocity increases on the whole atmosphere, and when it reaches the upper levels, this is 100 hectopascal, like 10,000 kilometers, 10,000 meters, by continuity, it goes to the Pacific, and there is a subsidence in the Pacific around this region. And this change, and this wind, when it reaches the bottom, it diverges. And this divergence of the winds produce a change in the thermocline, because the water start to be, there is a change in the way the water is spilled out in that region. So this produces a wave that travels to the east and is changing the thermocline and produce a El Niño or a La Niña event in this case, because it's very linear. When there is El Niño here, after there is a La Niña, and when there is a La Niña here, after there is El Niño in the Pacific. So we use a very simple conceptual model, as I told you, because conceptual models help us to understand the mechanism of work in a very easy way. So this conceptual model, it's called the Keynes-Ziviak model, is like an oscillator, and it only depends of the height of the mist layer, which is the first layer of the ocean, the height of the over the second layer of the ocean. You have the thermocline in the middle, and then you only consider the equator. So there are no latitudes, just the equator, and the east and the west. So this is an east-west profile and depth. So using this very simple model, you just have to initiate the model with anomalous winds. So the anomalous winds start to change the ocean and produce this coupling with the atmosphere. And these are the results we did with the simple model. This is the Keynes-Ziviak model, and a very more fancy model with a full developed ocean, which is the Nemo ocean model. And these are the observations. So these are the simulations for an interannual simulation. We ran the model for 50 years, and then we correlate the Atlantic SSTs with the rest of variables in the rest of the ocean. So here, there is a warming in the Atlantic Ocean, produce anomalous winds in the western side of the Pacific, and these anomalous winds produce a cooling. And here, this variable here is the thermocline depth. So this means that it's deeper here and shallow here, because this is negative, shallow here and deeper here. So this is in July, August, September. So there is an impact in the thermocline, but it's not very strong. And then in September, October, November, it gets stronger. And at the end, you have this tilt of the thermocline, which is deeper in the west and shallower in the east, and a fully developed La Niña in the Pacific. No anomalies appears in the Atlantic. So 6 months in advance, these anomalies are responsible of trigger anomalous winds that produce La Niña or El Niño in the Pacific. And these are the results with the model, in which we only use the anomalous winds that comes from the Atlantic. Because this model is done by, here you introduce observations, and here you run the model freely. And then you can see this shallowing of the thermocline here. The deepening of in the west is not so so well represented. But if you compare with a model of the ocean, a fancy model of the ocean, the results are very similar. So you can reproduce these results with a very simple model. And here we have taken advantages of the difference in the timing, because as I told you, El Niño in the Atlantic occurs in July, August, September. And in the Pacific, the El Niño or La Niña occurs in December, January, February, March. So there is a 6-month lag. So 6 months in advance, you can tell the people there is going to be El Niño, and you can predict it, and you can try to take advantages of the information for for many different problems that El Niño are associated with El Niño. So what we do is, with the Barcelona Supercomputing Center, they produce a seasonal forecast, and also with other models of these are all the models that produce seasonal forecasts. And the seasonal forecast consists in initializing in a particular month with the SSTs, just the SSTs you observe. You take a satellite or whatever, you have SSTs, you initialize with this information and run the model 6 months maybe, or one, there depends on the model, you run the model, and then there are different initialization of the model, and then you run to see what is going to happen. So in this first figure, what we found is if the skill is in terms of the correlation between observations and model. If the skill increases in the Atlantic, the skill in the Pacific increases. So if you have a good Atlantic, you can reproduce good the Atlantic, then you can reproduce in an adequate way the Pacific. And here is the same, but this is June, July, August in the Atlantic and June, July, August in the Pacific. This is with some lags. This is summer in the Atlantic and autumn in the Pacific. And this is summer in the Atlantic again, but December, January, February in the Pacific. So here we have these 6-month lags. And again, if you have stronger correlation, higher correlation in the Atlantic, good skill in the Atlantic, there is a good skill in the Pacific. Also, all the models, here is the relation between the Atlantic and the Pacific in all of the models analyzed. And in all of the models analyzed, the relation is negative. So when there is an Atlantic Niño, there is a Pacific La Niña. When there is an Atlantic La Niña, there is a Pacific El Niño. In all of the models, this is the observations, are models that are closer to the observations. Those are not so close, but all of them produce this negative correlation. And here is how, if the correlation between the Atlantic and Pacific is negative and significant, and it reaches higher values, how is the correlation with, how is the skill in the Pacific? How is the skill in the Pacific? So the stronger the correlation between the two basins, the skill on the Pacific is also stronger. So, well, in general, these results were saying that the Atlantic was providing a very good, a very convenient information for predicting ENSO. And, well, another important result is that, I don't know what time is it. Bien. Okay, so another important result is that we found that this occurs at in different decades. Here, nothing appears, and after the 70s, it appears. So it was the topic of the research of the PhD of Marta Martin, and she worked a lot in this multi-decadal modulation. Why in some decades you have this connection? Why in other decades there is no connection? But we are still working on this because it's a topic we have detected. We have done some diagnostic that are very coherent with natural oscillation in the climate we know, but we don't know what is going to happen for example, in the future with the increase of greenhouse gases. But for example, what we know is that in some decades in which the North Atlantic is colder and the South Atlantic is warmer, when this happens, the connection is stronger. This is the correlation between the two basins. This is the correlation between the two basins. We expect to have negative. So here there are negative, here there are negative. And this is the oscillation in the sea surface temperature in the North Atlantic. So when there are cold anomalies in the North Atlantic and warm in the South Atlantic, these two basins are connected. And we think that is a problem of the background state of the ocean. How are the ocean? The ocean are in a state that are stable or unstable. So if they are in an unstable state, all the winds that blows onto the first layer of the ocean produce changes in the SSTs and in the thermocline, and the El Niño and La Niña can be more active. But if you have a very stable thermocline and very deep, it's very difficult that the winds can alter it. So this happened under these changes in the SSTs of the global ocean. And so when there is this configuration, this is a schematic of this paper of Marta Martin, when you have this configuration, it's more, it's more, well, it's not more, it occurs disconnection, because when you have the other configuration, the connection does not occur. So this is more or less the same, but this is another paper in which a prediction, a statistical prediction of El Niño was done in different periods, and it was demonstrated that in the beginning of the 20th century and after the 70s, when there was an Atlantic Niño, there was a Pacific La Niña, and the prediction, if you do a seasonal forecast, is important to have the information of the Atlantic. But in these decades, they are totally disconnected. There is no information that you can provide to the Pacific to have from the Atlantic to have El Niño. This is very important because doesn't mean that there are no Niños in these decades. There are Niños, but are internally generated, maybe by stochastic noise, maybe by internal variability or other processes that comes from another basin, nor the Atlantic, nor the Indian Ocean, because they are totally disconnected. Indeed, there are other works that say that in the other decades, what occurs is that other basins are interacting. For example, here in this paper, what they say is that in the other basins, in the other decades, what happened is that the North Atlantic is impact of El Niño by another mechanism. And well, now there are two mechanisms that people in the community are discussing about how when the North Tropical Atlantic can be used to predict El Niño and when the Equatorial Atlantic can be used to predict El Niño, because they interact to the Pacific in different decades, but not, there are still some decades in which there is no connection, and this is another thing I'm going to show you here, because we use a complex network. We use a complex network in which we calculate what it is called the network distance, and it's based in a methodology of Chonis et al. And in this methodology, we take into account all of the possible relations: the Niño with the Atlantic, the Equatorial Atlantic, the El Niño with the tropical North Atlantic, El Niño with the Indian Ocean, the Atlantic in the North and in the Equatorial, all of the connections, possible connections between the different regions of the ocean. All of them in order to know what is the impact on ENSO. So we calculate like a network distance, and well, this distance, when it is close to the square root of 2, it means there is no connection. And when it has smaller values, it means that there is a strong degree of connectivity. So here are the results, and again, using different basins, at the beginning of the 20th century and after the 70s, there is a strong degree of connectivity because the values are around 1. And in these decades, there is no degree of connectivity because the values are very close to square root of 2, which is when there is no connectivity by definition. So here, what we did is the correlation between all of the basins, and we saw that all of the basins are connected. It's like there is a global mode in which all of the basins, the Atlantic, the Indian, the Pacific, are connected in a global mode, and this global mode produces stronger predictability of ENSO. Well, this result keeps independently of the database. Many people say, well, it depends on the database because some of the SST data comes from interpolation, and we don't have data in some decades. It's true that the data in the beginning of the 20th century over the Pacific are very scarce. There are not almost data. But we have done this also with different models of the CEMIT initiative, and we have found also that there are some decades in the models with strong connectivity, others with no connectivity. But what I can tell you is that the topic of tropical basin interaction is nowadays a new paradigm of research. Since these first studies in which we start to think why it's not isolated from the rest of the tropical basin, the tropical Atlantic, other research groups start to look not only in the Atlantic, but also in the Indian Ocean, in the different tropical basin, and they found that there are pantropical climate interactions that are not stationary in time. Sometimes all the ocean connect together, sometimes they are independent to each other. This occurs at different time scales. I'm talking about interannual time scales, but for example, at decadal time scales, there are also connections, for example, between the decadal variability of the North Atlantic with the decadal variability of the Pacific. And this is very important because it's something that it was not known before, 12 years ago, and it has strong implications. Some implications, for example, is that I don't have the figure here because we don't have the paper yet published. I couldn't have the paper. But we use data from malaria, from medical centers in the Sahel, in different medical centers. And we took this time series, and it was evolving very similar to that Atlantic equatorial SSTs, but also that the Pacific equatorial SSTs. And we do a map of a regression of this time series over the global ocean, and we found this Atlantic-Pacific connection. So we have to study more about this, but the impacts of the basin interacting in some variables that are very important from a social point of view is crucial because you can predict it in advance. Now in climate studies, it's very important a branch called climate services, in which you translate information from climate into other variables that can be useful for society. So, for example, in vector-borne diseases, in crop, for example, we work with people in agronomy. They have crop models from different species, and then what we do is to run the models with climate observations and see how the crop yield is going to change. And now we are in a project in fisheries in the tropical Atlantic, and we have found this Atlantic-Pacific relation with the fish in the tropical Pacific. So what we found is that when there is a warming in the Atlantic, the fisheries in the Pacific increase because it's colder, the Pacific. And if it's colder, it means that the water from the bottom rises with more oxygen, with more nutrients, because the upwelling produces nutrients and is very good for the all the trophic chain. So the implications of this pantropical climate interaction are very important because nowadays the ocean is one of the crucial predictors for the climate. So, well, this paper was published in Science in 2019, and it was a very important paper because they were like accepting at the end that the basins the Atlantic could interact on the Pacific, taking into account that before the 2000s, from an energetic point of view, nobody had looked at it. And well, also there is a book about interacting climates of ocean basins that was published last year. And there is this in the United Nations have this World Meteorological Organization. Like it has there is the World Health Organization. So there is the World Meteorological Organization, and in the World Meteorological Organization there is the World Climate Research Project. And this project has different sections, and one is CLIBAR, and CLIBAR put together scientists to talk about different topics of research. And the last 2 years ago, there was start this topic of research, tropical basin interactions, and we meet every other 2 months. We are planning people all around the world. We are designing experiments. We are going to analyze paleoclimate. For example, we are going to analyze data from coral reefs and also for sediments to see if these relations were observed in the past. There are going to be run models of paleo data and also in the future, because it's very important. The ocean are getting warming and warming. I mean, I don't know if you know, but we all talk about the 2 degrees, 3 degrees in the atmosphere in the next years, but nobody saw the picture of the ocean. And the ocean is warming is storing a lot of heat, and due to the thermal inertia, it has not released this heat. So although we stop emitting CO2 or greenhouse gases, the ocean is going to release the heat that already was stored. So this is one of the results for that on the IPCC was there are some impacts due to climate change that we cannot stop. I mean, there are some tipping points that they are already, the impact is already ongoing. I mean, it's not going to, it cannot be stopped. And one is the ocean, the heat of the ocean. And we are still working about how it will impact in many aspects of the circulation and impacts and regions of the world. And finally, this is 2002, this year. This is, I don't see, what is this? This is April. In April, there was some anomalies in the Atlantic. And then it has been, these are satellite images. And it has been developed an Atlantic Nino, and there is now a La Niña. We don't know the mechanisms. We have to do some simulation to see if the mechanism that produce the teleconnection between the Atlantic and Pacific works in this case, because there are also anomalies in the Indian Ocean and strong anomalies in the other regions of the ocean. But we think that most of the other anomalies are due to the atmosphere, so we think that there is this Atlantic connection on the Pacific that had produced the La Niña. And this La Niña is the responsible, as I told you at the beginning of the talk, of the anomalous anticyclone, one of the factors that has an influence in the anomalous anticyclone we have now here in the last 2 or 3 months. So, well, this is all. Thank you very much.
Thank you, Belén, for the presentation. So now we have time for questions or comments that you may have. Anyone? Yes. Wait a second. Yes.
English. Okay. Many thanks, Belén, for this nice talk. It's a good example of how the ocean-atmosphere exchange is an important part of climate variability. So what I have is a general question, which may have an easy answer. But so you've nicely explained how El Niño creates this temperature anomaly at the surface of the ocean. It cools the Western Pacific, it warms the Eastern Pacific, and how this drives these anomalous winds that feed back through atmospheric transport to the other side of the Pacific and also the Atlantic. These anomalies in the sea surface temperature can reach 2-3 degrees, which, as you well pointed out, is a huge amount, right? And not only drives the changes in the winds in the atmosphere, but also changes net primary production in the ocean by blocking, by ocean stratification, blocking the arrival of nutrients to the upper part of the column water, and also changes the transfer from the ocean to the atmosphere, from the atmosphere to the ocean of gases, right? So the general question is, those changes in sea surface temperature drive changes in productivity and the phase transfer of gases, and so creates a variability in the exchange of greenhouse gases like CO2, methane, N2O, but also ozone-depleting substances from the Western to the Eastern Pacific. And those then in the atmosphere could have an effect on the relative balance.
Yeah.
The question is, do you think that resulting change in the energy balance has any role to play in the atmospheric transport and the variability between El Niño and La Niña?
So if I understand you,
So this is explained from physical basis only, but these changes in sea surface temperature drives changes in gas and aerosols from the ocean to the atmosphere that would be very different between the Eastern and the Western Pacific, between La Niña and El Niño.
yeah.
Do you think those changes and the resulting effect on the relative balance could play any role?
Yeah, I understood you. So if you are asking me if the changes in the gases can have in turn a change in the teleconnection, for example. Well, I think that if there is a change in the warming due to the gases in the atmosphere, there is going to be a change in the pressure in the zonal gradient of pressure, so it's going to change the winds. I have not measured the difference in the impact because maybe they are negligible compared with the changes due to ocean. So I think that a nice experiment could be to compare simulations with or without gases and see if quantify this in a way. But I'm sure that they should have an impact, but I have not quantified. I don't know about the quantification of this difference. But also, as you were mentioned before the talk, the aerosols are also very important in the radiative balance. For example, in West Africa, the Saharan dust is very important. Also, the volcans are very important in the radiative balance, and a very important thing is that current models, they don't reproduce well the clouds. Some clouds, stratus over the ocean, are not well reproduced, so the ocean in these upwelling regions are very warm. And the stratification of the ocean is very strong, and the upwelling processes are not correctly simulated. So still, these models have some biases, and I don't know if we can quantify this. We should do a sensitivity experiment more than analyze these CP5 models, I mean 6 models.
More questions?
Well, I don't know if this is a silly question or not, but it seems that the variations are always in the east-west axis.
Yeah.
Is something there is something like that in the northwest, north-south axis, or is something that is related with the rotation of the Earth, or?
Well, there are Rossby waves that come from the conservation of the angular momentum, and then it calls vorticity, potential vorticity, which is due to the Coriolis parameter depends on the latitude. So when there is a warming in the Pacific, for example, there is upper level divergence, and the divergence occurs in all of the directions. So as I told you, we are analyzing this direction, east-west, and the impact in the Walker circulation. But in the other direction, what is happening is that the Coriolis parameter is changing. And when the Coriolis parameter changes, to preserve this quantity, anomalous rotational flow appears for conservation. And there it produces waves that reaches the North Atlantic, the North Pacific and North Atlantic, and also the South Pacific and South Atlantic. But the climate over this region is very non-linear because we have other internal processes, internal variability, and it's difficult to understand. For example, the teleconnection with Nino and Europe are not so linear. We cannot, are not so, there are teleconnection, but are different. There are different kind of teleconnection depending on how is the mini state, how is the internal variability, etc. So there are teleconnections, but the most linear one, and most that can be simplified better are those in the equatorial region, because you have the Coriolis parameter 0, and you're just working with a few variables. So this teleconnection works for this event. It works because we compare observation at this conceptual model, and it works. But it doesn't mean that the other teleconnections are not important. Can have an impact. Sometime we see a residual that maybe can come from the extratropical teleconnection. But in some, for example, we have used a recharge oscillator model, a very simple recharge oscillator model, not this, because this is a little bit more complex. And we have seen how in the last decades El Niño and La Niña are like almost a perfect oscillator. And we can very simplify the problem very easily without taking into account the external impact for other latitudes.
Thank you. I have a couple of questions. The first one is pretty obvious. Right, the Atlantic El Niño is a trigger for the Pacific El Niño. So, what would be the trigger for the Atlantic El Niño? What is the reason for it?
Yeah. Sorry, continue.
And the other one is, what I don't see is, maybe not, what is the actual mechanism that passes the energy from the Atlantic Basin to the Pacific Basin? Because something has to be there. Because the connection is easy to see in the data from a statistical point of view. And using a ray tracing approach, you can see the movement of the Rossby waves. That is the energy transferred by the Rossby waves. But I guess that the energy transferred by the Rossby waves is not enough to pass anything significant to the Pacific Basin. So something has to be there related to maybe to ocean transport, that is to the masses of water, actually. So I don't know the mechanism.
Yeah. About what is the triggering of the tropical Atlantic El Niño? There are many mechanisms that can work. One is from the Benguela region and the anomalous anticyclone. There is an anomalous anticyclone. Well, this global circulation, if you are in climate, you know there are the subtropical heights. And the subtropical, we have the Azores height in our latitude. So in the south hemisphere, there is the Santa Elena high pressure system. And when this pressure system changes, maybe internally or maybe due to a Rossby wave coming from the Pacific, when this anticyclone changes, it changes the alonson winds over the coast of Benguela, Namibia, Angola. And this alter the SSTs and produce a Rossby oceanic wave. And this oceanic wave travels from the east to the west, alter the thermocline in the ocean, and produce a warming. This is one mechanism. Other mechanisms are due to thermodynamic processes, not just altering the thermocline, but also altering the latent and sensible heat flux. So this is important, and also the radiative fluxes, because the clouds change due to the anomalous anticyclone, and the ocean gets warmer or cooler depending on how is the anticyclone. So locally, it's mostly due to the winds and the Santa Elena height. And it can be involved in dynamical processes like waves, but also thermodynamical processes due to radiative, the radiative balance, but also by the latent, the turbulent heat fluxes. Also, there are advection by currents that takes an important role. So normally what we do is a heat balance. So we calculate all of the terms of the equation of heat balance, the thermodynamic law, and what we do is to analyze what of the terms are more important in these events. And I could be a lot of time talking about this, because there are many works that say that in some decades the thermodynamics processes were leading the development of the modes, but in other decades it was more related to dynamical processes. I don't know if I answered you this. The first question. So this is local, but how the Santa Elena in turn get stronger or weaker? One reason could be the anomalous. It is called Pacific South American pattern. It's a Rossby wave in the atmosphere coming from the anomalous heating in the Pacific. So we are working now in a very nice thing, which is how the Pacific produced the Atlantic Niño, and how the Atlantic Niño produced the Pacific La Niña, and how the Pacific La Niña. So to try to understand this periodicity, which is very strong in the last decades, and maybe it's because there is this coupling between the oceans. And about the second question, I don't understand the last part of your question, because you were talking about the ocean transport, but to connect the two basins.
I can summarize in this way. If you have to give a responsible for the connection, let's say, how much would you put on the ocean latent heat and on the atmosphere? That is.
I mean, for the connection I have been talking about,
something like 40%.
Yeah, but I cannot answer how much is the ocean, because the experiments we have done, we prescribe the ocean, and we in one basin in the Atlantic, we prescribe the ocean in the Atlantic, and we put free the atmosphere and the ocean in the Pacific. And just with the Atlantic SSTs, we can trigger the RC interactions that produce El Niño. But it's true, the amplitude is not 100% reproduced. So yes, there are other factors that are having an impact. And maybe, for example, there is a leakage in the southern, that comes the water from the Indian Ocean up to the Atlantic. There is a leakage. It is very related to the westerly winds in the southern annular mode in the southern hemisphere. And there is a coupling between the ocean and the atmosphere there. When these winds shift to the pole, the leakage, the water start to enter into the Atlantic, and it has changed the properties of the Atlantic. And we, for example, this is another question that we are trying to understand, how the interaction from other basins through the currents, for example, this leakage, or for example, the AMOC, the Atlantic overturning circulation, how it impact in the background state of the ocean. Yeah, it's a very complex problem. But we can see that the oceans appear connected or disconnected, but we still need to know all of the factors that are playing a role here.
Thank you.
Any other question?
Well, thank you very much, Belén, for. I don't have a question, but a comment. I'm not familiar to this scientific field, but I am very interested in philosophy of science. And all along your talk, I have seen what to me are concepts which are very related to Thomas Kuhn. Is that correct?
Yeah.
Yeah, you talk about
Yeah.
normal science, paradigm change, new paradigm, and this raises many questions, philosophical questions. But just one question. So first, I'm correct?
Yeah, you're totally correct, because I omit that part. But in another talk I give in the Faculty of Physics to the students, I start talking about Thomas Kuhn. And this was because I like the idea of the change of paradigm in science.
Yeah, okay. And in this regard, did you somehow see some that in closely related fields, somehow this new paradigm has challenged their theories? Do they have to reinterpret their theories?
Yeah, if they have to review the previous theories, yeah, for sure. Yeah, I think so, because El Niño phenomenon was studied from a perspective very related to the Pacific, just from the Pacific, not taking into account other forcing. There was some physical constrictions due to, for example, the amount of heat that the ocean can stand, and how energy from other ocean could interact with the Pacific, that when I start, I remember that when I start talking about this result we had, they were all the time, this is not physically possible. It's like they were like, no, this is not possible. And what we found is that the Atlantic varies in a different season than the Pacific. So in a way, it's like, no sé cómo se dice en inglés, te pilla desprevenido. It's like the Atlantic acts when the Pacific is like not doing anything. It's like because the Pacific is active in our winter, but in the spring and in summer, the Pacific is not doing too much. So due to that, the Atlantic take advantages and have an impact in the Pacific. And this explanation was one of the explanations that could stand this energy. That the Atlantic energy could be transferred to the Pacific in a way, altering the Walker circulation. But it's true that I think, I mean, in this group, I'm going to show you the face. This person who's going to retire now that he doesn't want to retire. This person is the person who started putting the buoys in the 80s in the Pacific. Because before the 80s, there was no measure, only very small, only a few measures in the Pacific. And they put an array of buoys every other kilometers around the equatorial Atlantic. They go up to the bottom down to the bottom of the ocean, and they are measuring the temperature, salinity, currents, and El Niño is very well monitored. But before, it was very theoretical because there were some buoys. There were, for example, the southern oscillation was measured because there was an station in Tahiti and another station in Darwin in Australia. And they found this oscillation, the southern oscillation, between these 2 points, and all was simplified by 2 points after this array of buoys. Now we have satellites. And now we have Argo floats, which are some buoys that goes to you launch them, and then they start to measure, and when the batteries are off, they go to the bottom of the ocean, and they are in the bottom of the ocean, and now we have information of all of the ocean in 3D dimension, a lot of data. This is a very big data problem. And still, the results are very similar from the Pacific of what we already know. But in addition, we have the other basins, and we can say that they are doing something. But before, they simplified the problem with the Pacific. They put the buoys in the Pacific. Everything was in the Pacific.
Any other questions?
So, well, this person is very interested now in this topic because he is one of the father of El Niño, well, in currently research, and he's very interested in other external forcing because he was all the time just looking in the Pacific.
If there are no more questions, we thank you again for your presentation, but before, we have a small present for you.
Thank you very much. Muy bonita. Muchas gracias. Thank you.